Hello, my name is Roman Sadovsky and this is my physics and sport project. I will be looking at the physics of figure skating. There are so many things involved in figure skating and it's quite complex, so we'll focus on a jump. But before we begin, I would like to explain how the data collection took place. The video was taken from YouTube, which was a recent competition of mine, and this is the link. This particular jump is called the quad sal, and it involves the skater taking off backwards, rotating 4 times in the air, and then landing backwards. The video was made by a professional, however it was not yet appropriate for collecting data because the camera was not stationary, but following the subject, which was me. Therefore, a graph could not be correctly plotted. However, after using video editing software, Sony Vegas, the video was cut and stabilized to compensate for the camera movement. Also, the video was recorded going right to left, making it more difficult to graph, so I mirrored the image for ease of graphing using the same video editing software. After the video was imported into the graphing software called Logger Pro, this software enabled me to set the scale and plot points for my figure skating jump. I would first skip to the first frame where I'm just about to take off and then begin to plot points for every frame. Once I reach the last frame that I am in the air and about to hit the ground, I stop plotting points and set the scale. I drew the green line to represent the height of me with the skates, which is 185 centimeters. I then set the first point to represent time as 0 and set the origin. This software then generated a quadratic equation as follows. I then put the quadratic equation into Desmo's online graphing calculator. The software displayed the parabola as time in seconds and height in centimeters. The value for max height was represented at the top of the graph as the y value of 70.6 centimeters or 0.71 meters. For the length of time that I was in the air, I had to subtract the x values as the parabola did not start exactly at x equals 0. Therefore, the time in the air was about 0.70 seconds. So let's start with the kinematics. To make this simpler, I'll divide this situation into 2 parts, the approach into the jump and then the jump itself. Since we're looking at projectile motion, I will be focusing on the jump itself. First off, in kinematics, the x and y, or the horizontal and vertical component, are always treated separately. So vertically, or in the y, my max speed will be at the beginning and at the end of the jump. When I'm jumping, I have this vertical speed that I generated by pressing into the ice. But as I climb to the top, my vertical speed eventually reaches 0, but then accelerates back down to the ice because of the force of gravity. Therefore, I reach my second maximum speed right before I touch the ground. The only acceleration I experience in the y is the acceleration due to gravity, which is negative 9.8 meters per second squared. In the x, I have a constant speed that I generated on the approach. This proves to be projectile motion because there is no horizontal acceleration. So after data collection, I know that I will reach a maximum height of 0.71 meters and it will take me 0.70 seconds to achieve. Logger Pro also gave me the x displacement, or the resultant displacement of the jump, which was 1.98 meters. On the top right is a chart on the vertical and horizontal based on the data collection I've collected. First off, I want to start with finding the initial velocity in the y by using this formula. Although my resultant displacement in the y is 0 meters, I know that halfway I reach a height of 0.71 meters. Therefore, I subbed in the time for halfway, which is 0.35 seconds. So in the end, I end up with initial velocity of 3.74 meters per second in the y. Now using this value, I can find the final velocity in the y by using this equation. I end up with the same speed of 3.74 meters per second. This proves that maximum speed will be at both the beginning and end and shows that the initial and final velocity are equal. However, this is a scalar value and does not account for direction. Therefore, my speed is negative 3.74 meters per second because I'm going down at this point in the jump. Now I decided to find the final velocity in the x using a slightly different equation. I subbed in my x displacement and the time taken, and I end up with 2.83 meters per second. I then used this final velocity value to find the initial velocity. This is a slightly different equation than last time, but nonetheless, I end up with the exact same 2.83 meters per second. So the initial velocity in the x equals the final velocity in x. And the reason for this is because the horizontal velocity is constant. Now in the bottom right corner, I use these two newfound velocities to confirm the displacements. Now we can see here that we found all the other unknowns. Now that we're done with kinematics, let's move on to energy conservation. First off, let's go over some energy concepts. We first need to know what work is. The formula for work is force applied times distance. Work is done as long as a force is applied and a distance was made. For example, in my jump, I apply a force downwards to jump into the air and I make a vertical distance of 0.71 meters. If a force is applied but no distance is made, then no work is done. Also vice versa, if a distance is made but no force was applied and is just in constant motion, then no work was done. Power refers to the amount of work that you can do in a second. So if something takes a really long time, then you generated very little power. But if you did something faster, then you could generate more power. Now moving on, what is energy conservation? Energy conservation is the idea that energy is never created or destroyed. It transfers from one type of energy to another type of energy. For example, here is an energy chart for the jump. Now let's do some energy calculations. Like I said before, we're going to divide the jump into two parts, the approach going into the jump and then the jump itself. First off, let's calculate the kinetic energy skating into the jump. Logger Pro said that my speed into the jump is 3.8 meters per second. So I subbed it into the kinetic energy equation and I end up with 505.4 joules. Now keep in mind that this is the approach speed. Now for finding the kinetic energy in the jump, I used the previously found velocity, which was 3.74 meters per second, and subbed into the same equation. And then we end up with 489 joules. I then calculated the potential gravitational energy at the peak of the jump using the potential gravitational energy equation. And I end up with 487 joules. In theory, the kinetic energy at the beginning of the jump should be the potential gravitational energy at the peak. Now we can see here that the kinetic energy in the jump was 489 joules and the potential energy was 487. The reason these numbers are slightly different are because of slight variations that may have caused slight inaccuracies in the collection of data. So when calculating the efficiency of my jump, I use energy out as the kinetic energy in the jump, and then energy in as the kinetic energy on the approach of the jump. So then I end up with 96.7% efficiency. Now for work, I decided to calculate the amount of work done to bring myself to the top of the jump. And this should be equal to the potential gravitational energy. Therefore, work equals 487 joules. Now that I have this, I can find the force applied that I got myself into the air. Work equals force applied times the distance. So I subbed in my work, which I found earlier due to the potential gravitational energy, and the distance as the vertical distance of 0.71 meters. I end up with force applied of 685.9 newtons. Now using these values, I can calculate the power generated, and I end up with 696.7 watts of power. Now let's move on to forces. I'll have a video of the jump being played with free body diagrams on the side displaying what's happening. We start off with the glide into the jump. The glide into the jump, the normal force and gravitational force are balanced because I'm not sinking into the ice. And there's a very small friction force because ice has very little friction. Now I apply a force downward so that I can jump, but still the normal force is equal to both the gravitational force and the applied force. And now the friction force is increased because of the amount of force going down. This is a great example of Newton's third law of motion. For every action, there is an equal and opposite reaction. The amount of force of both the applied force and the gravitational force that's on the ice is pushed back into the normal force. Moreover, when I'm taking off, my toe picks are scratching in the ice, which is why the friction force is increased. Once I'm in the air, I'm essentially in uniform motion, and the only force acting upon me is the gravitational force. This is also a good example of Newton's first law. Every object in a state of uniform motion tends to remain in that state of motion unless an external force is applied to it. So I will be in the air and maintain the same velocity until an external force is applied to it, which is when I land. Then upon landing, I have similar effect as a takeoff, and on the glide out is similar to on the glide in except slower due to the loss of energy. Now let's do some force calculations. I decided to calculate only the forces of the glide into the jump. Through an online source, I discovered that the coefficient for friction of ice is 0.03. So by using the following formula, I figured out that the force of friction on the ice is 20.6 newtons. Now since while I'm gliding, I'm not applying a force, my F net is equivalent to the negative value of the friction force since it's working against me. Now by using Newton's second law, I can calculate the amount of acceleration, or in this case deceleration, caused by the friction force. After calculating for acceleration, it turns out that my acceleration is negative 0.29 newtons per kilogram. Now this is a very little amount of deceleration, and this is because ice has very little friction. According to Newton's second law, the acceleration of an object is directly linked to the mass. So if I happen to be lighter, my acceleration would be larger. But if I were heavier, my acceleration would be lower. The main sporting equipment we use in figure skating are figure skates. So let's talk about how these skates influence these concepts. Figure skating blades are made up of two parts, the blade and the boot. The blade is also made of two parts itself. The part that glides on the ice is made out of stainless steel, and connecting it to the boot is aluminum to keep the weight lower. The boot is made out of plastic, rubber, and other synthetic materials. Both materials are made for strength and weight in mind. Clearly, our boots need to handle heavy amounts of force, and they must be durable enough to handle the weight of the skater and the forces applied to the boot. The synthetic design of the boot helps absorb any vibrations, which reduces any energy loss due to sound. Although the toe pick causes a lot of energy loss, we know that ice has very little friction, and we know on the takeoff of the jump, the toe pick digs into the ice and causes more friction and loss of energy. Although this can seem like a bad thing, this helps the skater control what they're doing since ice is so slippery. The boots are designed to be as lightweight as possible. We know in Newton's second law that if mass is lower, then acceleration is higher. So the lighter weight equipment helps the skater accelerate more. This is the conclusion of my Physics of Sport project. Thanks for listening.